Hi, good morning. Welcome back to reinforcement learning. The last session we have seen what is n-step temporal difference learning. In this small discussion, we are going to extend n-step TD to TD lambda. It is a more general temporal difference learning developed by Richard E. Sutton, the author of reinforcement learning textbook. In the last two sessions, we have seen what is temporal difference learning and TD0. What are the characteristics of this temporal difference learning and its extensions, etc. But now we are going to develop a new algorithm that will really unify our temporal difference learning and Monte Carlo learning. We have already seen what is a Markov decision process and its learning properties, and its Markov decision process prediction, Markov decision process control, etc. Now, at present, we are in temporal difference model. That means the time difference makes sense in the case of agents learning. Once again, you have to compare this MTP and TD. In TD, we are more focused on the time difference learning. The temporal difference error, that is more important because it will give more insight to the agent while it learns from the environment. Naturally, we will continue this TD lambda in its online and offline mode. This online mode is, as in the case of TD, it is alpha lambda. Naturally, the offline mode is Q lambda that we will see in the coming sessions. In this short video session, we will look into the transition from n-step TD to TD lambda, how we will convey all the information that we captured through an n-step TD to a TD lambda in such a way that it will contain all the good informations from a Monte Carlo and also the temporal difference approach. Then we will see what is the concept of lambda return. In order to start this journey, we need a simple but a new concept known as lambda return. Then some mathematical representation for this lambda return. As in the previous cases, we will discuss some backup diagrams, and finally we come to the core part of temporal difference learning and its advantages over other reinforcement learning, that is the unification of TD and MC. The temporal difference learning and the Monte Carlo learning characteristics can be unified with the help of this TD lambda by just changing this learning parameter lambda. It will have another name. This lambda will have some other name, namely eligibility, the trace decay. That is discussing eligibility traces is known as trace decay parameter. This lambda is known as trace decay parameter. It will say to what extent it is a TD algorithm or to what extent it is a MC or Monte Carlo algorithm. So TD lambda has average of n-step TD return. That is the main highlighted theme of this session. What is TD lambda? TD lambda has a return, but that return is not usual return. What is the difference? It is average of n-step TD return. That means the last session we will see how to generate n-step TD return. That means we start from a state ST and look forward to the later state's return and calculate its discounted sum, that is G, T, T plus N. That means return from the state T to T plus N. T plus N means n step forward. Now we are utilizing that n-step return in the form of average. Then there is a natural question why we are taking average. The answer is so straightforward and all of you are familiar with, because in your plus 2 classes, when you start the first experiment in your physics lab, you will do, for example, the simple pendulum experiment. You will make that experimental setup, then just allow that particular string to make it in the pendulum action. Then you just make use of the length of the string and also the time. You calculate the acceleration due to gravity at that particular place. You may get different values corresponding to acceleration due to gravity. It may vary from 9.2 to some 11.7, something like that. 9.2 meter per second square means the acceleration due to gravity at that particular place is 9.2 meter per second square, like that. If it is 11.2 something, that means it is very high compared to our gravitational constant 9.8 meter per second square. Then you have repeated that experiment 10 times, and your instructor asks you what is gravity acceleration due to gravity at that particular point. What is your answer? You just tell all these answers or take the average. If you start telling all these answers, your instructor asks you why you are telling all these answers. Naturally you say it is the output I obtained during this my experiment. Then he will tell you just take the average, and it is the average acceleration due to gravity. Why we take average? We are familiar with the procedure, then why we take average? The simple and the most popular answer is average is a good measure for a group of values. If you have 10 values related to a particular experiment, then this average will a group measure, or it is called a measure of central tendency. Measure of central tendency. If you take this average, most of the data in that group will come around this average. That is the idea. According to Fisher's statistics, average is an unbiased estimate. This consistent to most all characteristics of good estimate is satisfied by this average. I repeat, most of the good characteristics of a good statistics is satisfied by this simple average. That is why we are using average everywhere. If you try to incorporate that idea into reinforcement learning, in the last session we have seen how to extend one step reward into n step reward with the help of n step TD. We just calculate g, t, t and t plus n step reward ahead, but this is just a sum of n later state returns, but it need not be a good measure for the entire group of n values. So we apply statistical measure, we take average of these n different rewards. That is called the lambda return. Then how we will take this average? There are two possible ways. One is simple average, that means calculate individual values and divide it by total number of values. Total by total number, that is simple average. There are other options like weighted average. Here we are using weighted average, the special type of weight. That weight is the powers of lambda, the lambda raised to n minus 1. We are using lambda raised to n minus 1 for this weighting. Then I scaled it or normalized by a quantity 1 minus lambda. Then why we are using this normalization? The normalization are basic techniques in statistics, because we try to develop distributions from raw measures. I repeat, we try to develop distributions from raw measures. If we are going to take simple average or weighted average, we are trying to compare this new measure into a distribution. Distribution means some mathematical function like that. Here also we are trying to develop a weighted average, but it should have some good characteristics of statistical distributions. We will see in next slide. Then what is TD lambda update? See lambda here. Now the temporal difference is explained in terms of lambda. Then what happened to the weight update formula? First we look into that. Our usual weight update formula is V of st equal to V of st plus alpha into the current expected value, that is RT plus 1 plus gamma into V of st plus 1 minus V of st. That is our formula. Here this GT lambda actually corresponds to our previous temporal difference target, and this Vt plus n minus 1 of st gt lambda minus this expression. This difference is called temporal error. We are trying to update the state value using the temporal error. That is the idea. We simply revisit that concept of temporal difference in temporal difference learning approach. Now, how this lambda is incorporated? When we look into this formula, lambda is here. So instead of our TD return, I am using GT lambda. Again, GT lambda is a return, but there is a lambda in the role. So this is known as GT return, lambda GT return, or simply lambda return. So TD lambda update is defined in terms of lambda return. Instead of one step return, I am using a lambda return. Then how we can define this GT lambda? Answer is here. This GT lambda is a cumulative sum. It's a weighted average. Then this defined as 1 minus lambda into sum over n equal to 1 to infinity lambda raised to n minus 1 g t t plus n. We are familiar with this term. This is n step return. N step return. This n step return is weighed by lambda raised to power. Then it is scaled by a factor 1 minus lambda. In order to understand this role of 1 minus lambda into lambda raised to n minus 1, we look into a simple infinite series. Okay, first of all, think this expression. This 1 by lambda is common, that why I take this 1 by lambda outside the sigma. For simplicity, I just take this 1 minus lambda inside this expression. So this expression becomes sigma n equal to 1 to infinity 1 minus lambda into lambda raised to n minus 1 g t to t plus n. Now we take the sum. When lambda is equal to n is equal to 1, what you get? 1 minus lambda into lambda raised to 1 minus 1, that is lambda raised to 0. So we got the first term 1 minus lambda. Second term is we can take 1 minus lambda common outside again. Then when n is equal to 2, we got lambda raised to 2 minus 1, that is lambda. When n is equal to 3, this coefficient becomes lambda raised to 3 minus 1, lambda square. Then next is lambda cube, next is lambda raised to 4, etc. The summation varies from 1 to infinity. Then you just take sum of these power, lambda power, what you get? First term is 1 plus, second term is lambda plus, third term is lambda square plus, fourth term is lambda cube plus, etc. 1 plus, lambda square plus, etc. We are familiar with the result. 1 plus x square plus, etc. is equal to 1 by 1 minus x provided by mod x less than 1. When we use that, we got 1 divided by 1 minus lambda. Outside we have 1 minus lambda. So 1 minus lambda into 1 by 1 minus lambda is equal to 1. That means total weight of these weighing parameter is equal to 1. I repeat, total weight of this weighing parameter 1 minus lambda into lambda raised to n minus 1 is equal to 1. So in effect, this is a weighted average. This is a weighted average. So GT lambda or the lambda return is a weighted average. Now once again look into here. This weighted average gives the is similar to a probability because its value is always lies between 0 and 1 and total value is equal to 1. In that sense, we can compare this sigma n equal to 1 to infinity 1 minus lambda into lambda raised to n minus 1 gt to tn plus 1 as in the form sigma n equal to 1 to infinity p of x into x. Sigma n equal to 1 to infinity p of x into x. Instead of n, you can choose x. Sigma x equal to 1 to infinity p of x into x. That is expectation. That is my aim, is to convert this sum, this sigma, in the form of an expectation. That is a statistical measure. Okay. In short, this lambda return is the expected return with some weighting. The expected return with this weighting. This weight will give some additional quality in calculating this return. We are already familiar with some type of parameters in return, like discounting rate. In that case, we just calculate discount of a single return, just return of an action. But in the case, it is not like that. It is the return from a state. We weight the return from a state with the help of this parameter lambda. I repeat, discounted return and this lambda discounted return are different. This is called the lambda return because it is weighted based on the parameter lambda. but that weighing is not on individual return of actions. It is based on the effective return from a state, the state-wise return. We are focused on state-wise return. This return gt lambda is called the lambda return. So that is why the term lambda come into role. Okay. Now we look into role of lambda in TD lambda. How we can use or interpret the use of lambda in TD lambda definition, the TD lambda learning definition. Now look into this backup diagram proposed by Richard Sutton. This is one step return. In that case, the coefficient is 1 minus lambda. I repeat, this is my one step return. That means the state st is updated with a single state value and the corresponding coefficient is 1 minus lambda. Here, how many state values are used for the update? State 1, state 2 to get update for this initial state. So this is two-step return. In that case, I am using the coefficient 1 minus lambda into lambda. In the case of 3, I use 1 minus lambda into lambda square, etc. At the end state, I am using lambda raised to t minus 1. Then the sigma means sum of these coefficients. We have already seen sum of this coefficient becomes 1. So this 1 minus lambda into lambda raised to t minus 1 or lambda raised to n minus 1 in general form a probability density function. More clearly, probability mass function, because this is a discrete distribution. That is the idea. Everywhere we trying to create distributions from random measures or random values. We start with the mathematical definition, then convert it into the form of a routine established statistical parameter or a statistical measure. That is the idea. So when it starts from one step return and leads to some t step return. So TD lambda defines MD from, not MD, TD, temporal difference from one step to n steps or t steps, whatever it may. So this lambda will help us to give more insights to temporal difference model. This lambda is a very good parameter that defines length. So in one step, it is 1 minus lambda, two step 1 minus lambda into lambda. Now what happened to this weight parameters when we move from left to right? This is the coefficient 1 minus lambda into lambda in second two step update. In one step update, it is just 1 minus lambda. Now take the ratio 1 minus lambda into lambda by this 1 minus lambda. I repeat, take the ratio 1 minus lambda into lambda by 1 minus lambda. We got lambda. Again do that thing here. 1 minus lambda into lambda square divided by 1 minus lambda into lambda. We got lambda. Because these coefficient become a geometric progression. It gives the common ratio lambda. So it is decayed by lambda. As it moves on, decayed by lambda. Initially 1 by lambda, then 1 by lambda into lambda, because lambda is less than 1. That is why we call it is decayed. Is decayed by lambda. So role of lambda in lambda return. Then what happened when we apply this expression, this weighted distribution for gt lambda? What is the role of lambda in defining this gt lambda or lambda return? Now look, at initial state in the back diagram, initial state the coefficient is 1 by lambda. It is the largest one. At state t, the next return is rt plus 1. So at initial state or the starting state, it gives higher weightage. That means the immediate state return will give higher weightage. When we move to the next state, it is decayed by lambda. So later state will be decayed properly. In that way, it calculates the n step return. The n step return is calculated using such weight. We will not take the average in the full values. We will take the average based on this decayed parameter lambda. That is the idea. That means later step return gives small or less importance to this. In the case of our discounted factors, we do this. That is only for the return by an action. For a particular action, we do that. This for the state return. That is the difference. Then this discounting has some more meaning related to human learning. For example, suppose a student in my class did a particular job in a fabulous way. I will give him a chocolate or give him a gift to and reinforce that particular performance, or give us an encouragement like that. If I do it the correct time, it has more value. Suppose he did that action in 5 days before, and I will give him a chocolate only after 1 month. Then what happened? He may get some level of reinforcement, I agree, but the level of reinforcement is not up to the level at which he got at the exact time, at the exact context. That's the difference. It's something like to the present value of money that we have discussed in our finance. So reinforcement at right time is more important. If an action get reinforcement in later state, it is discounted. It is very important to know that it is only to that particular action, not to the state value or state return. If this happened to that particular action, it is called discounted. Discounted return correspond to that action. Certain incorporate new idea, he will discount. We can call it as decay, the state-wise return in the lambda return with the help of this weighted parameter 1 minus lambda into lambda raised to n minus 1. It's a brilliant job. In that way, we can find out the weighted average of n step returns, and it will make the learning more effective or meaningful. Now, lambda return with the post terminal states. We are taking this n step TD lambda. Then from that formula we formulate this lambda return or GT lambda. So after the terminal state, we proposed from the state T, I start the process and I stop at T plus n. That is my one stretch. After that, I am considering the original return. It will not be considered for decay. Only n state returns will be considered for n step TD return. Then I calculate average of this n step return only. Beyond that, I will create the same return. So it can be written in this form: gt lambda is equal to 1 minus lambda into sigma n is equal to 1 to t minus 1. Because we starting from initial value 0, so t minus 1 gives the terminal state. Lambda raised to n minus 1 gt to tn plus 1 n state return plus. Beyond that, that means after the nth state, we will take the same return by a discount lambda raised to t minus 1. That's all. This formula will give you more meaning. Okay, we will try to answer this question. What happened when lambda is equal to 1? What happened when lambda is equal to 1? What gt lambda gives? First of all, we look when lambda is equal to 1, what happened to this formula? When lambda is equal to 1, this term 1 minus lambda becomes 0. So this dominant sum becomes 0. Now we got this 1. 1 raised to any number is 1. So we got gt. So gt is actually the return, the complete return of that particular state value system. State, action, reward, value system. It is our generalized MC, generalized Monte Carlo model. So when lambda is equal to 1, in this system, it will give Monte Carlo. When lambda is equal to 0, what do you get? When lambda is equal to 0, what do you get? There is a natural tendency to put lambda equal to 0 here. When lambda equal to 0 here, what do you get? 0 raised to a power. So 0 raised to a power is equal to 0. So 0 into this expression becomes 0. Here also 0. 0 into another expression 0. That is a natural mistake people think. But remember, here n stands from 1 to t minus 1. Initial value of n is 1. So initial value of lambda in this sum is lambda raised to 1 minus 1. That is lambda raised to 0. That is 1. So before substituting lambda equal to 0 in this sum, you should expand the sum. So when n equal to 1, we got lambda raised to 0 into gtt plus 1 or gtt plus 1. The remaining terms contains powers of lambda. So when lambda is equal to 0, this outside term 1 minus lambda becomes 1, so this is just unity, and this sigma becomes just gt t plus 1, one step return. So when lambda is equal to 0, this gives one step return. That is why td0 is known as one step td, or a one step updation will happen. So based on lambda, again we can generalize temporal difference laning. Definitely lambda varies from 0 to 1. When lambda equal to 0, this gives td0, one step value updation will happen. When lambda is equal to 1, it goes to our Monte Carlo distribution. So we get a more good parametric definition for temporal difference laning, and it will unify both Monte Carlo and temporal difference laning. When lambda is equal to 0, this is td0. When lambda is equal to 1, it automatically goes to our Monte Carlo, generalized Monte Carlo laning. So the whole class of reinforcement laning under temporal difference model and also Monte Carlo laning will come into the same group. That is the advantage of using this TD lambda notation by Richard Sutton in reinforcement laning. The real unification of Monte Carlo laning and TD laning will happen in these TD lambda settings. Okay, we have seen what is GT lambda when lambda is equal to, that is just one step at a time. So this is all about the generalized form of TD lambda as a unification for temporal difference laning and the Monte Carlo family of laning. In the next session, we will see both SARSA and Q lambda together. SARSA, as you have seen in the case of temporal difference laning, is an online laning approach, but Q lambda, definitely it is offline. We do the same approach, but it is a lambda return happened in online and offline mode. That's all. We just extend the concept of TD laning into a more general setup with the help of expected value of lambda return, expected value of n step return, that is called the lambda return. So we are introducing a new term or a new concept of lambda return, and it helps us to develop a new update formula for TD lambda, and this TD lambda will unify all the laning approach from the class of Monte Carlo and temporal difference laning. Okay, thank you very much for watching.